Now, for us to look at chemical and physical processes and think about them in terms of electrochemistry, there needs to be an understanding that there is in fact this movement of electrons which is occurring in the process. And you might think, well, isn't that the case with all chemical and physical processes? Aren't there electrons that are moving? Actually, to get a sense about whether that's true or not, what we need to be able to do is to look at some of the reactions that we're familiar with. Like here is a sodium chloride becoming a sodium ion or a chloride ion. Here is some water dissociating to make protons and hydroxides. Here is some water as a liquid becoming water as a gas in a physical process. Notice that in each of these examples right here, there is a way to define how much change is occurring in terms of the electrons sitting inside each of the atoms. And that way of describing them is this thing we call oxidation number. Oxidation number gives us a sense of just exactly how many electrons reside on that particular compound. We know, for example, that in this case right here, the sodium ion is deficient in electron compared to sodium metal. And so we say that it's got one fewer negative charges, so it's got a positive one for its oxidation number. The chloride has a negative one for its oxidation number because it has one more than would be predicted from its place in the periodic table. Same thing occurs down here, a +1 for the proton. Down here, we've got this overall charge which is sitting on this compound, which is -1. Somehow I need to add up the charges on the oxygen and the hydrogen so that they equal a negative number here. So when you think about where the electron goes, electronegativity arguments told us that that electron, if it's going to go anywhere, would tend to want to go toward the oxygen. How much would want to go toward the oxygen? Well, the oxygen wants to be noble gas-like. So in wanting to be noble gas-like, it would gain 2 electrons. And the hydrogen, in wanting to be noble gas-like, would lose an electron. And what do you know? The two values add up together, -2 plus +1 makes a negative sign overall. Well, I can make those sorts of arguments also for neutral compounds here. Let's take a look at sodium and chloride right here. Overall, the charge on this is neutral, so whatever it is that's taking place in terms of the charge sitting on these atoms, it has to add up to equal this neutral value here of 0. Well, I know that sodium wants to be noble gas-like by losing an electron. And I know that chlorine wants to be noble gas-like by gaining an electron. What do you know? You add those two values up, they equal to 0. Down here, the same argument. Each of the hydrogens wants to lose an electron to be noble gas-like. The oxygen, wants to gain electrons to be noble gas-like. The interesting thing to see in all of this is what happens overall to these changes in oxidation number as I look at these compounds. Notice the +1 for sodium becomes +1 overall, -1 and -1, +1, +1, +1 for the hydrogens, -2 and -2. These all stay the same. Notice that in each of these 3 examples of a solubility problem, the dissociation of a salt and water, of an acid-base problem, and in terms of a physical process, there has been no change in the oxidation numbers. When there's no change in the oxidation numbers, that means my electrons are not moving. If my electrons are not moving, then I'm not going to have the opportunity to do electrical work. I may be able to do physical work. We already talked about P delta V work for something like this, but I am not able to talk about the work associated with electrons that are added to or leave a particular chemical compound. That electrical work is associated with what we know to be much more substantial kinds of energies. The energies associated with changes in covalent bonding, for example, hundreds of kilojoules per mole sorts of arguments, as opposed to values that are down on the 5 and 10 kilojoule per mole basis. So these are typically going to be lower energy sorts of processes, even here with water dissociating. And in contrast, what happens when you do electrochemistry is a place where there is a change in the oxidation numbers. If there is a change in the oxidation numbers, that's when we're doing electrochemistry. That's when we're able to do the work that produces batteries, for example.